Okay, so solved problems for chapter 26. First we have a parallel circuit with 4 resistors. We know what 3 of them are, we don't know what that is. And we hook an ohm meter across this guy and we measure the equivalent resistance of the entire circuit to be equal to 2 ohms, and we're asked to solve for X. We know for resistors in parallel we can write the equivalent resistance as such. I've just done that to save us a little bit of time. So essentially we're solving for this R1, we're going to call that guy to be X. So we can rearrange this equation to say 1 over X is going to be equal to negative 1 over R2 plus 1 over R3 plus 1 over R4 minus 1 over the equivalent resistance. So that's going to be equal to negative 1 over 15 plus 1 over 5 plus 1 over 10 minus a half. So we're going to get 1 over X is going to be equal to positive 0.13 repeating. You take the inverse of that and we solve for X, and it turns out to be 7.5 ohms. Okay, a sample problem for breaking down or for simplifying circuits to solve for currents. We have 4 resistors here. I'll call them 1, 2, 3, and 4. And we're asked to find the current in each resistor. We have some battery that doesn't have any internal resistance. So what we can do is we can take this circuit and we can break it down into a circuit that's going to look like this, where I've combined those resistors in parallel. So I've combined R1, 2 and R3, 4. What we can do is we can say, well, we know that these resistors are in series, so R1, 2 is simply going to be R1 plus R2, which is going to be equal to 1 plus 3, or 4 ohms. We know that R3, 4 also going to be in series, so R1, R3 plus R4, or 7 plus 5, is going to be equal to 12 ohms. So I know that this guy is 12 ohms and this guy is going to be equal to 4 ohms, and I have 48 volts across each resistor. I could break this down further using resistors in parallel, but it turns out I actually have enough information right here to say, you know what, I know that the voltage drop across R1, 2 is going to be 48 volts. It must be. It's going to be 48 volts across R3, 4, so now I can just straight up apply Ohm's law and say V is equal to I12 R12 and solve for I12. I12 is going to be equal to the voltage divided by R12, or 48 volts divided by 4 ohms, and I get that it is equal to 12 amps. What that does is that tells me I have 12 amps flowing through that equivalent resistor right there. I must also have 12 amps flowing through R1 and 12 amps flowing through R2. So I1 is going to be equal to 12 amps, and I2 is going to also be equal to 12 amps. Now we'll say similarly that I3, 4 is going to be equal to that potential drop across R3, 4, or 48 volts divided by R3, 4, 12 ohms, and I'm going to get 4 amps. So I have 4 amps going across this circuit right here. That tells me that I also have 4 amps going through R3 and 4 amps going through R4. So I3 is going to be equal to 4 amps, and I4 is going to be equal to 4 amps. So here we have a simple RC circuit. We have 3 capacitors and 1 resistor, and we're going to have the switch closed, and we're asked for, how long does it take until the capacitors have lost 80% of their initial stored energy. So really what I'm looking for is, I'm looking for when the potential energy is equal to 20% remaining of the initial potential energy, therefore I've lost 80% of the energy. I know that there's a relationship between potential energy and charge for a capacitor, Q squared divided by 2C. So I can say this is going to be Q squared divided by 2 times capacitance is equal to 0.2, and then this is going to be the initial charge squared divided by 2 times the capacitance. Capacitance is going to cancel out. I also know that there's going to be a relationship that describes my charge as a function of time for discharging capacitors. My charge is going to be equal to my initial charge, e to the minus t divided by RC. So I'm going to take this guy and plug that in right there, and I'm going to get Q naught squared e to the negative 2t divided by RC. Essentially I've distributed the 2 right there. Is going to be equal to 0.2 Q naught squared. Now I can cancel those Q naught squares. And essentially I'm just going to solve this guy for t. I'm going to take the natural log of both sides. That's going to get rid of my exponent. And I'm going to have negative 2t divided by RC is equal to the natural log of 0.2. Go ahead and I multiply both sides by RC, divide both sides by negative 2, and I'm going to get my time is going to be equal to negative RC divided by 2, natural log of 0.2. I know what my resistance is, that's 25 ohms. Now I need the equivalent capacitance for these capacitors. So I'm going to say, well, these capacitors are in series, so I can write 1 over CEQ is going to be equal to 1 over 15 picofarads plus 1 over 20 picofarads plus 1 over 10 picofarads, and I'm left with 1 over CEQ is equal to 0.2216 repeating inverse picofarads. So I go ahead and I invert that guy, and I get CEQ is equal to 4.61 picofarads. So now I have everything I need. So I'm going to have negative 25 ohms. I'm going to have my 4.61 picofarads divided by 2. I'm leaving the pico in there, and I'm just going to keep in the back of my head that's 10 to the minus 12th, natural log of 0.2, and I'm going to come up with a time that's equal to 92.9 pico seconds, where I've kind of carried that 10 to the minus 12th through the calculation. And lastly, we'll get some practice using Kirchhoff's rules. This is advertised as a one-dot problem, and really it's quite simple, but the math gets a little bit tedious, shall I say. Before I talk about the junction rule, to simplify the problem, let's talk about the loop rule just very briefly. I have 3 unknowns, I1, I2, and I3. That means I need 3 loops to give me 3 equations to solve for those 3 unknowns. You can choose your loops however you want. You can choose to do that loop, you can choose to do the loop in the opposite direction, you can choose to do this loop right there. Really it just has to be a closed loop, so there's really many possible ways to solve this problem. All will lead you to the same answer. Let me talk about the junction rule real quick. We've gotten 3 currents. Let's take a look at this junction right here. We've got I1 coming into it and I3 coming into it, so that tells me that right here I'm going to have I1 plus I3. Let's take a look at this junction right here. I have I2 coming out of it, or coming into it, and I3 leaving it. So that tells me that my current right here is going to be I2 minus I3. It's kind of coming like that right there. So my junction rule has simplified it. Now I don't have 5 currents running in my problem. So let me choose my loops. I'm going to choose to do that loop. I'll call that loop 1. Choose to do that loop. I'll call that loop 2. And I'll choose to do that loop, and I'll call that loop 3. So let's go ahead and do the loop rule. I'm going to start loop 1. I'm going to start it right here and go and work my way that way. So the first thing I get is I'm going from the positive end to the negative end of that battery, so I'm going to get negative 12 volts. I'm going to go across the resistor number 2. I'm going in the opposite direction of the current, so I'm going to say this is going to be plus I2 multiplied by the resistance. It's going to be 1 ohm. I'll write it in there, why not? And then I'm going to keep on going, and I'm going to cross over the 5 ohm resistor, and I'm going in the opposite direction as the current, so it's going to be a plus, and then it's going to be, the current's going to be I2 minus I3 multiplied by my 5 ohm resistor. So that was loop number 1. I can go ahead and I can rearrange this equation right here to give me I2 is going to be equal to 2 plus 5, 6 I3. You'll see why I do that in just a second. So now let's go ahead and take a look at my second loop. And again, I'll start my second loop right here. First thing I do is I go across that EMF source. So start my second loop. I'm going to start off with a positive 9 volts. I'm going from the negative side to the positive side. Now my loop is going in the same, is going over this 8 ohm resistor in the same direction as the current. That means I'm going to subtract off this I1 plus I3 multiplied by 8 ohms. And I'm going to come back around to I1, or to the 1 ohm resistor, and I'm going in the same direction as the current, so again I subtract off I1 multiplied by 1, and this guy must be equal to 0. Forgot to say that on this one. This guy here must also be equal to 0. So I can go ahead and I can solve this guy, and I'm going to write it in the language of I1. Here I can say I1 is equal to 1 minus 8/9 multiplied by I3. And lastly, let's go around loop number 3. Just to make it easy, I'm going to start right down here, and I'm going to say, okay, first thing I'm going to do is I'm going to go across my 10 ohm resistor. I'm going in the same direction as the current I3, so I'm going to have a minus I3 multiplied by the 10 ohms. I'm going to keep on going. I'm going to go across this 9 volt battery. I'm going in the opposite direction, so I'm going to subtract off that 9 volts. I'm going to cross over this 1 ohm resistor right there. I'm going in the opposite direction of the current, so I'm going to add I1 multiplied by 1. And I'm going to hit this guy right here, subtract I2 multiplied by 1, and lastly I'm going to go across this power source in such a manner that I'm going to add 12 volts. That guy's going to be all equal to 0. So if you take a look at this equation right here, here I have I3, here I have I1, and here I have I2. If I go ahead and I stuff this expression for I1 in terms of I3 into this, and I take this expression right here and I stuff it in right here where I have I2 in the language of only I3, I can rewrite this equation where I only have I3. That's going to allow me to solve for I3. I'm going to leave the details up to you because I definitely don't have enough room on the slide. I'm going to come out with I3 is equal to 0.171 amps. Now what I can do is I can say, well, here I have my expression for I1 in terms of I3. I simply need to plug I3 into that. I can get what I2 is. I2 is going to be 2.14 amps. And lastly, same type of deal. I take this I3, I plug it in right there, and I get what my I1 is. My I1 is going to be 0.848 amps. I also have a nice little extra segment where I show you how you can use matrix manipulation on how to solve 3 equations, 3 unknowns.